back into that for sure.
We're starting to get into that with biology.
With biology? Oh, good for you guys. That's fantastic. Yeah, has to do with the Guinness Brewery. They tell you about that yet? That's good stuff. Anyway, we'll get to it. Now, in class, we collected some data yesterday, which I probably lost because I was hoping one of you guys brought it with you. We did some penny spins, and we were trying to estimate what is the probability that a spun penny lands heads up. Now we had a guess. What was the guess that we had? 50%. We said 50%. 0.5, because why would it be any different than flipping a coin? That was the kind of guess. I'll put a question mark in there, because that's a guess. It wasn't a statement. I mean, we can't really prove that a flipped penny is 50-50, except for the fact that we see it every time we do the experiment. It's kind of like, you know, proof by demonstration, or proof, quote unquote, by demonstration. So in order to answer this question, what we did was, we went in, and we collected some data. Yes, we took what I'm going to term a random sample, if you will, which I gave you guys a bunch of pennies. They were all pre-2006. I don't know if you noticed that or not. They changed the face of the penny in 2006. They've got like an offset Lincoln face now in front. The back looks a little different. It's got a shield, I think. I still use the old ones, and there's a reason for that. There's a reason for that. I haven't gotten enough of the new ones, number one. And number two, well, we might have to compare and contrast. Maybe that'll be a final project or something. But they're all pre-2006, but they're all the same kind of penny. What was our data? How many spins did we do? Allie, go ahead if you don't mind.
The whole thing?
If you don't mind.
We had the 0 through 10. You want that?
Oh, not even that. No, not even that. Just how many times did we, as a class, spin?
5.
But how many? You each spun 10, yeah? 270. There was so we had 270 total spins. 270 total spins. How many came up heads? 112. Thank you, friends. Thank you. That's all the data you're going to get from this experiment. And what's cool about it is that's all the data you need from this experiment. There's a lot of power in those numbers, as long as you're convinced those numbers are a fair representation of what's actually going on with the data. And we'll get into that. We'll get into that too. So now the question was, how do we estimate the answer to this? Well, we did one more thing, I believe, correct? We did one more thing with these two numbers. We made it a percentage. Just like we did back with the binomial distribution, we turned it into a probability by saying, what is the probability in the sample of getting heads? Now, there's a difference between the probability in the sample of getting heads and the probability in the population of getting heads, isn't there, right? The probability in the population we call little p, probability. What do we call the probability in the sample? Do you remember its name? P hat. P hat. I didn't bring it. I should have brought it with me today. It's in my closet. P hat. And simple calculation. It's one of my favorites in mathematics. X over n. It's one of the more common measures you'll see in the news, in Gallup polls, in Quinnipiac polls. Go ahead, Allie.
That was the population?
Sample. Yeah. You never know what your, thank you for this point, by the way, Allie. You'll never know your population's value of p. Never. Because it's too big, right? In order to get the p, little p, probability of getting heads, we'd have to spin pennies infinitely. And let them all fall infinitely, and then count infinitely. See how that's impossible? Completely impossible. Ridiculous to even talk about. So this is definitely a sample proportion. Yes, thank you. That cannot be said enough. Yes. Well, I'm going to revisit that idea with more detail on the PowerPoint. I got like a note slide set up so that in case what we're talking about in class gets forgotten, you've got it residually in that place. Okay, for us, that was 112 out of 270, which came out as
41.48.
41.4. Let's call it 41 and a half, if that's okay with you guys. 0.415, which means 41.5% heads in our sample. And if we worked for a major news organization, we would say, stop the press! We got news! When you spin a coin, you're going to get heads 41.5% of the time. Now, this is ridiculous, of course. It's a stupid thing to say, right? But think about it this way. Suppose you were testing the results of a neonatal drug, and the percent increase of a certain condition was 41.5%, based on the sample you just took. The news media would say, stop the presses! The incidence of hives is 41.5% greater than it was before. It's the same exact thing in a more realistic context, right? But to both of those statements, what do you say as statisticians? What's margin of error? Yes. Because that is a function only of the sample you just took. It's a purely descriptive statistic. It is a purely descriptive statistic, which means you guys spun 270 times and you got 112 heads. If I had you spin 270 more times, do you think you get 112 heads again?
No.
Probably not. Almost no chance. You think you get close? Probably close, assuming nothing really crazy deviant happened in our sample. I mean, there's a possibility that all of you spun and they hit the corners of the desk or something and something happened. But assuming no goofy deviation, we're probably going to get close to that, right? So let's just do this. Let's just do this for a second. We know that p hat is 41.5%. We know we have to have, I'm pull this down for a second so we don't need it right now. We know we have to have a margin of error, correct? We know we have to have a margin of error. And what I want to do first is just make sure, before we actually get into the strict calculation of said margin of error, I want to make sure you remember how to apply a margin of error correctly, if that's okay with you guys. So the first thing we have to do is remember what a margin of error is. M-O-E for margin of error. Let's give it some values. What are common margins of error that you guys see in the news? In Gallup polls, in political polls, in research articles that you've seen?
Plus or minus 2%.
Plus or minus 2%, Ben, thank you. Plus or minus 2%.
5%.
5%. Any other ones that you guys have seen? 4? Yep. They can be very high. They can be as high as 15%, honestly. It all depends, as you'll see, if not today, definitely on Thursday. Depends on how large a sample that you drew. It depends only on that, and the measure of confidence, which we'll get into today. Now let's just make sure we know how to apply these. I'm not saying any of these is the actual margin we should use in our particular experiment. We can calculate that, and we will calculate that, I promise you. But I want to make sure before we blindly calculate it, that we know how to use the actual margin once we know what it is.